All right, so today we're doing 2-1. We're starting the first new unit, so make sure you're paying close attention here. Let's get started. We all know that the standard form of a polynomial function is just, simply put, let's just keep it simple, highest degree to lowest degree, and all like terms combined. Let's keep it simple. So, for example, 4x cubed plus 3x squared plus 5x minus 2 is in standard form, highest degree to lowest degree. The 4x cubed part's the cubic term, 3x squared is the quadratic term, 5x is the linear term, and then -2 is the constant term. We all know what standard form is, right? So the reason we wanted to review standard form before we get to what we're doing is because you name a polynomial by degree and the number of terms. So if it's not in standard form, then you're going to name it wrong. So this is how we classify or name a polynomial. We give it two names. The first name is by the degree. The second name is depending on the number of terms. So this chart's already on your worksheet for you, if you'll notice. And this is how we'll name a polynomial. When I say classify the polynomial, it just means name it. Okay, so if we have degree 0, such as x to the 0 power. If we have x to the 0 power, that would create a constant, right? 5x to the 0, isn't that just 5? So the first name is from degree, like I said, so that would be a constant. Now, if it's degree 1, x to the first, it's linear. If it's degree 2, it's quadratic. Degree 3, cubic. Degree 4, quartic. The way I remember this, quartic is just a little trick. I mean, it's kind of dumb, but 4 quarts in a gallon, right? 4 quarts in a gallon. So when I see degree 4, that's how I remember quartic. Does that make sense, everybody? A little trick. And then quintic, degree 5. If it's an x to the 5th power, it's degree 5. Now, you guys are too young to remember this, but there was a show on the Disney Channel about this mom who has 5 babies at once, and there are people in the real world that have twins. It's called having twins. So that's how it's easy for me to remember because I watched this Disney show called Twins, and that's what it was about, was 5 babies. So quintic, that's hopefully a helpful way to help you remember quintic. So the first name comes from the degree. And then the second name comes depending on the number of terms you have. So if you have one term, it's a monomial. So do you see how 5 would be a constant from x to the 0? So it's a constant, and then there's only one term, so it's a monomial. So another example of a monomial would be simply like x squared. That's only one term, right? That'd be a quadratic monomial. So monomial means one term. If there's 2 terms, then it's a binomial. Does everybody see that? So this would be a linear, degree 1, binomial. Are we all comfortable with how we're naming these? So if I had x cubed plus 2, isn't that 2 terms? That's a binomial. 2 terms means binomial. So we have 4x cubed. How many terms is that? 1, so it's a monomial. 4x cubed minus 2x squared plus x. There's 1, 2, 3 terms. That would be considered a trinomial. Triangles have 3 points. Trinomial, kind of an easier way to remember that. You guys get what I'm saying here, okay? And then this one has 2 terms, so it's a binomial. And then look down here, we have 1, 2, 3, 4 terms. And after that, there's no special names. So it'd just be polynomial of 4 terms. Yes. So the degree is classified by the highest. Yes, great question. So I should have been more specific. We always name it by the highest degree, and then we'll count the number of terms. So the first name comes from the highest degree, and then we'll count the number of terms. So we have for number of terms, we have monomial, binomial, trinomial, and then after that, no special names. Polynomial of 4 terms, polynomial of 5 terms, polynomial of 6 terms. Do you see how that goes? After degree 5, it's just 6th degree, polynomial of 2 terms and whatnot, okay? So let's just name it. It's pretty easy. You'll have to memorize the chart, but once you get naming these, you'll have it memorized pretty quickly. So let's name these 2 really quick. These are my examples. Just look. First, we need to put it in standard form, 9x squared plus 3x plus 5. So now let's classify the polynomial. So we have degree 2, which is quadratic. And then there's 1, 2, 3 terms, so it's a trinomial. Pretty easy, right, guys? Okay, pretty easy. Is that bugging you? If you can hear it. I'm so sorry. All right, and then let's do this one. We have x to the 4th, and then we have, let's combine our x squared. So we have plus 4x squared, right? And then we have plus 4x minus 12, so let's name it. Highest degree is 4 quarts, and again, it's quartic, right? Quartic. And then this is a polynomial of 1, 2, 3. It has 4 terms. There's not a special name for that. The quartic, and we'd say polynomial of 4 terms. Did you guys see how to classify a polynomial? Okay, let's just get to the good stuff then before I don't know if you're going to practice that in a second, but let's get to the good stuff. All right, so now we're going to talk about end behavior and turning points of many different functions. So this is also on the front of your packet, if you'll notice, but you might want to take some side notes if you need. So the degree, okay, good, I'm recording. The degree of a polynomial function affects the shape of its graph, which makes sense. The degree of a polynomial is going to affect the shape of the graph, right? If it's quadratic, we know it's a parabola and it's a smiley face, right, everybody? Or a frowny face, depending. So continuing that, and it also determines the maximum number of turning points. Right now, that's not going to quite make sense. When we get to the examples, it will. And turning points, guys, are places where the graph changes direction. So quadratic has 1 turning point. Do you see how it would be decreasing and then it changed? Right there's a turning point and now it's increasing. So turning points are where it changes direction. Does that make sense, everybody? Pretty straightforward. It's where the graph turns. Okay. It also affects end behavior. So end behavior, guys, is what your graph is doing to the far left and to the far right. So with that being said, end behavior is pretty easy. You just look with your eyes at the graph and then you can determine, you can look and analyze the end behavior. Do you all understand what I'm saying when I say end behavior? Where the graph is growing to the far left and right. If not, when you see the examples, you will. So I just wrote that a little bit simpler. The degree affects the shape and the max number of turning points the graph can have, and you'll understand why in just a second. And then we look at the leading coefficient to also see where our end behavior is going to go. So we'll look at the degree, and we'll look at the leading coefficient to determine what our end behavior is. We look at degree, leading coefficient to determine the end behavior. Degree, leading coefficient to determine the end behavior. Degree, leading coefficient to determine the end behavior. So these are the first 2 examples of 2 different types of end behavior you're going to see. There's 4 total types of end behavior. Here's some examples of 2. So let's just look at this first one. We have 4x to the 4th plus 6x cubed minus x. If I was to graph this on a calculator, it would look like this. Now the end behavior in this case is up and up. Does everybody see how to the far left my graph's going up, to the far right it's going up? That's the first type of end behavior, up and up. Does everybody see that? Okay? And then notice some things here. This is degree 4. If you were to graph this on your graphing calculator, you would see that you have 1, 2, 3 different turning points. Okay? Does everybody see the turning points? We're all good with what a turning point is. Now, one thing that we asked calculus was, what are the students lacking in? Because you'll go to calculus next year. What are the students lacking in on their knowledge? And they said they struggle with seeing limits. So instead of determining end behavior like this, which we're going to do both, we're also going to practice it in calculus notation. So I want to make a point, guys. If this is my x-axis here, isn't this, if I keep going, so here's my x-axis, if I keep walking this way, eventually I'm going to end up at positive infinity, which isn't a number, it's like a place. Our brains actually can't comprehend what infinity really means. So, but right, everybody listen, this is the x-axis, right? If I'm walking this way and I keep walking, aren't I eventually going to approach positive infinity? Right? Now, if I walk this way on the x-axis, I'm eventually going to approach negative infinity. So we all understand that on the x-axis. Now, this is the y-axis, which is also called the f of x axis, right? F of x is y, function notation, right? If we go down, 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 eventually we're going to approach negative infinity. And if we go up, 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 we're eventually going to approach positive infinity. So right now we're going to do some calculus notation. So it says, as x approaches positive infinity, so as our x values are going to positive infinity, where's my function growing to? Where's my function growing to? As x approaches positive infinity, where's the function growing to? Positive infinity. Does everybody see how calculus notation is going to work? So as x is approaching negative infinity, where's my function growing to? It's up and up. Nope, look, as x is approaching negative infinity, where's my function growing to? Positive infinity, right? That's true for up and up. Does that make sense? Okay, let's keep going. So with degree 4, the maximum number of turning points it can have is 3. Because these are both, notice, degree 4 is an even end behavior, right? Everybody? Degree 4 is an degree 4 is an even degree. All even degree functions have the same types of end behavior. It's either up and up or down and down. Just like isn't a quadratic also even? Doesn't a quadratic always have up and up or down and down? All even degrees, end behavior is going to work the same. So see how this one has up and up? Well, it's degree 4, so it has same end behavior, and then this is positive, so it's up and up. Just like on a quadratic, if it was x, let's say it was 3x squared, if this is even and positive, won't that look like that? Do you see how the end behavior is working the same for degree 4 and degree 2? Okay, all even end behavior will work the same. Yes? If I'm understanding your question right, odd end behaviors have opposite end behaviors, always, and we're going to get to that in just a second. Yep. All right, so let's look over here at this quadratic, guys. Even degree, right? So it has same end behavior. It's either up and up or down and down. Well, we know that if there's a negative in front of a quadratic, it flips it upside down, right? So it's going to be down and down. Does everybody see how this is the example of end behavior down and down? All right, so let's determine our end behavior in calculus notation for the quadratic. So as x is approaching positive infinity, where's my function growing to? Negative infinity. Do we have questions on that? You guys are in limits right now, which is a calculus topic. So as x is approaching negative infinity, where's my function growing to? Negative infinity. Very good. Now quadratics always have one turning point, right? You can't have a quadratic without a turning point, right? Okay, and it only can have one. Okay, very good. So it has one turning point. I have a note up there for that. And then we're also going to determine the increasing and decreasing intervals. So guys, increasing and decreasing intervals. Just look at the graph and look where it's increasing and decreasing. So look with me on this 4x to the 4th plus 6x cubed minus x. Aren't we decreasing till we hit that turning point? Now think about it, guys. If you're decreasing, boom, you hit the bottom, you're no longer increasing or decreasing, right? Just like if you walk up the stairs and you reach the top, you're now no longer increasing or decreasing, right? So turning points are not increasing or decreasing. Is everybody good with that? Okay, awesome. So we're decreasing till we hit that turning point, and then aren't we decreasing right here as well? Okay, so we have that, and then we look at this on this interval, from this turning point to this turning point, we're increasing, right? And then from this turning point to positive infinity, are we going to continue increasing? Okay, awesome. We'll do an example where we get really specific with these in just a second. Right now, we're just getting the feel for what end behaviors look like. These are just the even end behaviors so far. So even end behaviors have up and up or down and down. All right, and then this one right here, we're increasing. We hit our turning point. We're no longer increasing or decreasing. And then after that, we're decreasing. So are we feeling a little bit comfortable with end behavior for evens? It's either up and up or down and down, right? If it's positive, it'll be up and up, right? That's what keeps it up and up. If it's negative, that's where it flips it upside down. Okay, so we're good with turning points. Now, I wanted to say one more thing. Sorry, one more thing. There's just so much with this. So degree 4 has at most 3 turning points. Now, here's why. We have 1, 2, 3. If we were going up and then all of a sudden we curved back down, that would be 4 turning points, right, guys? Would that be able to be even end behavior? No, because it's not the same end behavior. So do you see how degree 4 can have at most only 3 turning points? Okay, awesome. Here are some examples of odd end behaviors. So let's just look at something really basic as y equals x cubed. Now notice, you read it from left to right. We read end behavior from left to right like a book. This is an example of down and up. Does everybody see it? Now if you look at this, y equals x cubed, we're increasing. Do we ever have a turning point here? Nope. So this one we are strictly increasing. There are no turning points. Does everybody see why? It's strictly increasing. So we would write on that strictly increasing. Okay, good. And then let's go ahead and write our end behavior in calculus notation. Yes?
So you would write,
I would take either. Yes, because you're right. It is increasing right on the interval from negative infinity to positive infinity. Great question. So let's go ahead and write out it in calculus notation, our end behavior. So as x is approaching positive infinity, where's my function growing to? Positive infinity. Now as x is approaching negative infinity, f of x is approaching negative infinity. All right. Now looking over here, this is an example of up and down end behavior. So it has opposite end behavior up and down. This is another example of a cubic. So we're looking at y equals negative x cubed plus 2x. This is end behavior up and down. And then as x is approaching positive infinity, where's my function approaching? Negative infinity. As x is approaching negative infinity, f of x is approaching positive infinity. Now this is a degree 3 with 1, 2 turning points, right, everybody? 2 turning points. So we have 2 turning points. And degree 3 has at most 2 turning points, 1 less, just like with degree 4, right? Because think about it, if we started coming down and then turned again, wouldn't that make it an even? Does everybody understand how we can only have at most 2 turning points for degree 3? Not all degree 3s have 2 turning points, it's at most 2. So right here we have a degree 3 with no turning points, right? You see that it's just at most 2 turning points. Okay, awesome. So just, I'm going to erase that real quick. Yes.
So this if we got rid of that,
it had no turning points. Yep, it would have looked like, I can't draw it very good right now, but yes, like that, right? Strictly decreasing. Does that make sense? Yeah, because that negative is what, and I'll talk about that in just a second. Yeah, good question. The answer to that is yes. If we took away the 2x, then it would be strictly decreasing. Right, yes. All right, so this is increasing on this interval, right? And then it's decreasing, I'll change colors on this interval. So we'll write out those intervals in very gory detail in just a second. All right, so I want you to notice something about odd degree functions. They have odds, have opposite end behavior. End behavior works the same for all odds. So don't we know what a line looks like? Isn't that a positive line? So isn't the positive line's end behavior down and up, right? And what makes it positive is, like, if we have y equals like 2x, for example, the 2 is positive, right? That's what makes it a positive line. So look in front. Do you see how that's positive? That's what made the end behavior work the same as this positive line. So if you know what a line looks like, you know what all odd end behavior looks like. Does that make sense, everybody? So look over here. Do you see how this has up and down? If we have a negative line, because it's also an odd end behavior, doesn't it look like this?
Yeah.
A negative? So do you see how it's up and down?
Yeah.
So if you know what a quadratic looks like, even, and you know what a line looks like, odd, then you can use that for all even and odd functions and behaviors. So let's do, so that's that in general. So like I said, even degrees, end behavior is the same. If it's positive in front, if it's a positive in front, like 1, it's going to be up and up. If it's negative in front, it'd be down and down. That's all you need to know is for quadratic, you just need to know how a quadratic looks. And then for odd degrees, it has opposite end behavior. And if it's positive in front, it'll be like a positive line, so it'll be down and up. If it was a negative in front, it'd be like a negative line, so it'd be up and down. Questions on that? Yes.
So does it matter, like, on the, like, the x squared and the, like, does it matter, like, if it was 4x?
Good question. It wouldn't matter if, let's say it was 4x to the 6th. We would say, oh, it's even end behavior, so it's up and up or down and down. Then we look at the front, it's positive, so it's up and up.
Okay.
Good question. Yep, very good. All right, so let's just do some quick examples right here. It says, consider the leading term of the polynomial. What's the end behavior of the graph? So we look at it. Is this even or odd? Degree. Odd. So we have opposite end behavior, right? Now, is it positive in front? Yes. So this is going to look like a line. The end behavior is going to behave the same as a line. A positive line looks like this. So won't this end behavior be down and up? Perfect. So now let's write it in calculus notation. As x is approaching positive infinity, f of x is approaching positive infinity. Are we all seeing it, or do I need to explain that in further detail? As x is approaching negative infinity, f of x is approaching negative infinity. So next example here. We look at the next one. We see, oh, it's degree 4. It's even. So that has the same end behavior. It's either up and up or down and down. It's a negative in front. So it's going to be like a negative parabola end behavior, right? Yeah. Yeah, that's fine. This is what's really important. So then as x is approaching positive infinity for this down and down, f of x is approaching negative infinity, right? And then same here. All right, we're good. Okay, so I think you're good. We're not going to keep going with that if you understand it. You do? You need more examples, yes.
So if it was the other way,
like negative x cubed?
No.
Oh.
The graph was like side to side instead of up and down.
Oh, I see what you're saying. No, you would just say from left to right. So you'd still say up, because that's still growing up and down, right? Good question. You're saying if we have something that looks like this, that would still be because it's growing up? Oh, no, I see what you're saying. It's growing this way and this way forever. Oh, but it's growing up forever and it's growing down forever, right? So, no, this would be up and down.
Oh.
Yeah. Yes. Number 3. We go up the leading coefficient. We go up the leading term. Yep, so this is degree 6, so it's even, right? And then it's negative, so won't this be down and down as well? Okay, this one's odd, right? Positive, so won't that be like a positive line? So down and up. So we're good with that, right? Okay, sweet. So this is what I want you to do is grab your calculators real quick. It says, what is the graph of each cubic function? I'm going to have us just focus on this one. So looking at this first one, isn't this one strictly increasing? Okay, this one has no turning points. And the increasing interval is from negative infinity to positive infinity. I'm showing you how to write out the intervals. The decreasing intervals, there's none, because it's strictly increasing. All right, and then you guys are understanding that, so we're going to skip past that. What I want you to do is look. Now we've got to get specific. So we have 2 turning points on this, right? The end behavior is up and down. We could go through this, but I know you get that. So the turning points, I'm going to write out what they are. My turning points are at over 1 up 2. Over 1 up 2. Does everybody see that? My other turning point is negative 1, negative 2. So now we've got to be really specific. When it says what's the increasing intervals, I'm going to write that out. Isn't this my increasing interval? Isn't it increasing? We go off of x. Isn't it increasing from negative 1 to 1 on that interval for x? So our increasing interval is from negative 1 to 1. Does everybody understand why that's the interval in which my function's increasing?
Yes.
Okay. And decreasing intervals. So we have this decreasing interval. It's decreasing till boom, it hits that wall, right? So it's coming in from negative infinity and it stops decreasing at x equals negative 1. Does everybody understand? We do a parenthesis because it's not including negative 1. Now we're also decreasing from that wall, and we're talking x, right? Make sure you're not mistaking it for down. We're talking x. Interval is x. So our decreasing interval starts from 1 to positive infinity, right? Isn't that also where it's decreasing? 1 to positive infinity. Questions on that? So do you see how we're going to get specific with the increasing and decreasing intervals? Okay. Because it's x intervals. All right, so go ahead and do these problems and check with me. Oh, you know what? I want to do problem notes. Wait, just a sec. Well, I thought I added that in there. Just a second. I want to do one with you with your calculator. Go to problem number 5, everybody. Type that into your calculator because I have to show you something. Everybody type in problem number 5 into their calculator and pull up your calculator. I'm going to show you how to use your calculator. Nobody knew this the first hour. So So go to y equals, type in number 5. I'll do it with that. I'll just show you how to get the correct intervals for this. So type that into your graphing calculator, number 5. Do we all have that function typed in? This is the X key right here. You look, okay? Good graph, everybody. Now, if you can't really see your graph very good, go to window. I'm going to go to window right up here. If it looks a little bit stretched out or a little bit you can't see enough, hit window. I made my window smaller so I could get in closer. So I made my X min, that means as far down as I want to see on my X, so I made it -5. X max, I made 5. I don't need to see much further than -5 and 5 on X. Then X scale means that we're working in ones, so I'm going to leave that. I always leave that usually. And then Y min means as I need to see as far down as -5, so I put -5, and then my Y max is at 5. That's just so I can get in there closer. Does that make sense, everybody? Now, look right here. Look on your graph right here. So hit graph again. Right here is a turning point, and right here is a turning point. If I said to you, what are the intervals where it's increasing and decreasing, don't you need to know those exact turning points? Now, notice those are not falling on an exact spot. We need to use our calculator to find those exact values. So this is how you do that. Now, I want you to listen really closely. Is this a relative minimum? Meaning it's a minimum, but it's not the whole, like obviously this is growing forever downwards, right? So the min is -infinity, right? So this is the relative minimum of the graph. This is the relative maximum. So just remember that those are mins and maxes. So we're going to find the minimum value so we know our turning point. So you'll do second, trace, go to minimum, hit enter. Now this is the minimum value. If you do not do this part right, your calculator will give you the wrong point. So it says left bound. We need to be left of the minimum, anywhere left. So take your arrows, scroll left. Now look, I don't care as long as I know I'm left. It doesn't matter where. You see how I'm left of the min? I hit enter. Now it says right bound. I need to scroll anywhere right of the min. You see how I'm to the right of it? So I hit enter. Now it says, do you want me to guess? We do want our calculator to guess. We gave it the correct bounds. Hit enter. So we have a minimum, and your values are not going to be pretty. This is the first example. We have a min at -0.51, comma 1.23. Write that down. You have a min at -0.510. Oh, let's just do 2 decimal places. So -0.15, comma 1.12. There's our min. Now let's find our maximum. Let's find this other turning point. So you're going to have to redo it, but now you have to do max. So we're going to go second, trace, and go to maximum. Now it says left bound. We have to be left of the max. The max is right here, so anywhere left will work. You see how I'm just randomly choosing right here? Does everybody see what I mean? Okay, hit enter. Now it says right bound. I'm going to scroll with my arrows, and anywhere right will work. That's good enough. Enter. Do you want me to guess? Yes. So we have a max at 0.36, comma 4.1. So now you can go ahead and say your increasing and decreasing intervals. So let's think about it, guys. Isn't this decreasing from 0.36 to positive infinity? That's one of our decreasing intervals, right? Right? Isn't that the x value for this point? It's decreasing from 0.36 to positive infinity, yeah? Yeah. Do you guys see what I'm saying? Why we would need those points? And like why our calculator will give us the exact points. Okay, are we all good? I just want to make sure that you're all set. I don't want you to feel lost. Okay, let's practice and then I can help you one-on-one. So these are the problems you're working on now. Sorry about that. You're working on 1 through 6, 9 through 15. Check with me as you go. A lot of the same questions. So remember, we are increasing. If you have something that looks like this, isn't this the only place that we're increasing? So it would be between that x point and that x point, right? Okay, so just a reminder. We're now able to determine the least degree. We're able to determine the degree. We're able to determine the number of turning points, right? The most number of turning points. And we're able to determine end behavior, right, everybody? Okay, now, Next thing, and this is on the front, let's see, is it on the front of your thing? Okay, this piece isn't, so if you need to take notes somewhere, do. But now we have to be able to determine the degree of a polynomial. So what this says is, suppose you were given a set of polynomial function outputs. So if we're given a bunch of outputs, remember, if you plug in something, we're going to get something out, right? So outputs are y values, right? Everybody? Inputs are x, outputs are y. So it says, you know that their inputs are an ordered set of x values in which consecutive x values differ by a constant. So what that really means, that makes it sound really complicated. It doesn't. It's not, though. If we have a set of x, y points and our x's differ by a constant, for example, 1, 2, 3, 4, 5, 6, aren't they all differing by 1? Okay, if that is happening where these x values are differing by a constant, then you can determine the degree of a polynomial by taking differences of your y values. So we're going to look at our y values and analyze them. We're going to take differences of them, and you can determine the degree based on the differences. So everybody listen. If you take differences of your y values, and the first time they come out, those differences come out to be the same, then it's linear. Let's say you take differences of those y values and it's not the same the first time. And you say it's not linear. Now you'll take those new values and take differences again. Let's say the second time you take the differences and they're the same. Then it would be quadratic. You guys see what I'm saying? If it wasn't the same, then you take differences of those values again. Now the third time, like in the bell quiz, right? Weren't in the bell quiz, the third time they were all 24. That would have been a cubic because it took us 3 differences to get the same. Does that make sense? Okay, now you can only do that if your x values are differing by the same amount. So if your x values are all over the place, you can't use this method. Does that make sense, everybody? So here we go. It says, determine the degree of this polynomial. Because, right, so these are the x, y values that if we plugged in, we would get into the polynomial we're about to find. But really this is just asking us what's the degree. Are our x values differing by the same amount? Yeah, so we can go ahead and take differences of our y values. Now you always take the difference of the y value that comes before the one above it. Did you all hear that? So let's all carefully do this, because if you get even one wrong, your whole thing's wrong. -7, okay, so everybody pay attention, walk me through this. -7 minus -1. -6, right? -3 minus -7. +4, right, guys?
Oh, yeah.
5 minus -3. 8. See, if you even mess up on one sign, your whole thing's going to be wrong. 11 minus 5. 9 minus 11. -7 minus 9. -18. Did we take all those correctly? Were they the same the first time we took? 11 minus 5, right? Are we good? Oh. Yeah, 11 minus 5 is? Are we all good?
Yeah.
Are we? This is -16.
Yes.
Okay. Sorry about that. Okay, guys, so they weren't the same the first time, so it's not a linear polynomial. So let's take differences again. You have to take the differences of the y values that come before the one above it. 4 minus -6. 10. 8 minus 4. 6 minus 8. -2 minus 6. 16 minus -2. -14. Were they the same when we took differences the second time? So it's not quadratic. Let's continue again. 4 minus 10. 4 minus 10 is -6. -2 minus 4. -6. Guys, be really careful when you're doing this on your paper. It sucks to get and not do it right. -8 minus -2. And -14 minus -8, -6. Do you see how we have to take differences 3 times and now they are the same? So we would say this is degree 3. You guys, these values came from a cubic. Do you all understand that? Pretty easy, right? You mess up on one subtraction back here, the whole thing is wrong. Okay? You saw that in the bell quiz, so be really careful. All right, I'm not going to do any more. Ready, set, go. Finish the worksheet. The rest of the time is yours.
Does the worksheet go